Today we are going to learn about simulating data distributions using numpy. We will explore how to generate, visualize, and apply various statistical distributions using numpy's random module for analytical needs.
Welcome to our tutorial on simulating data distributions using numpy. In today's session, we will delve into the world of statistical distributions, a crucial aspect for anyone involved in data science, machine learning, or any form of quantitative analysis. By simulating data distributions, we can perform hypothesis testing, create predictive models, and assess risks with greater accuracy. We'll be utilizing numpy's powerful random module to generate a variety of distributions, visualize them using matplotlib, and discuss their applications in real-world scenarios. Stick with us, and by the end of this video, you'll be equipped with the skills to simulate and analyze different statistical distributions for your analytical needs.
Let's begin our exploration by understanding what statistical distributions are. In simple terms, a statistical distribution describes how the values of a variable are distributed. It provides a mathematical function that explains the likelihood of different outcomes in an experiment. The most common distributions include the normal distribution, also known as the Gaussian distribution, which is characterized by its bell-shaped curve. It's widely used due to its properties and the central limit theorem. Then, we have discrete distributions like the binomial distribution, which models the number of successes in a fixed number of independent Bernoulli trials. The Poisson distribution, another discrete distribution, is often used for modeling the number of times an event occurs in a fixed interval of time or space. Understanding these distributions is essential as they form the basis for statistical inference, predictive modeling, and are extensively used in machine learning algorithms to model real-world phenomena. The normal distribution is perhaps the most important distribution in statistics, often referred to as the bell curve due to its shape. It's defined by two parameters: mean, average, and standard deviation, spread. To generate normal distribution data using numpy, we use the numpy.random.normal function. This function allows us to specify the mean, standard deviation, and the number of samples we wish to generate. For instance, if we wanted to generate 1000 samples from a normal distribution with a mean of 0 and standard deviation of 1, we would use numpy.random.normal 0, 1, 1000. Once we have our samples, it's crucial to visualize them to understand their distribution. We can easily do this using matplotlib, a popular plotting library in Python. By plotting a histogram of our samples, we can visually confirm that our data follows a normal distribution. Normal distribution data is widely used in various applications, including finance to model returns, biology to model traits, and in quality control processes. Next, let's explore how to simulate binomial distributions using numpy. The binomial distribution is a discrete probability distribution that models the number of successes in a fixed number of independent Bernoulli trials, each with the same probability of success. It is defined by two parameters: the number of trials, n, and the probability of success, p. NumPy provides a straightforward way to simulate binomial distributions through the numpy.random.binomial function. For instance, if we want to simulate 10 experiments of flipping a fair coin 20 times, we can use numpy.random.binomial 20, 0.5, 10. This will give us an array of results showing the number of heads, successes, in each experiment. Visualizing the results using a histogram can give us insights into the likelihood of different outcomes. Binomial distributions are crucial in fields such as quality control, where they help assess defect rates, and in digital marketing for A/B testing to determine the effectiveness of different strategies. The Poisson distribution is a discrete probability distribution that models the number of events occurring within a fixed interval of time or space. It is characterized by a single parameter, lambda, which represents the average number of events in the interval. NumPy provides the numpy.random.Poisson function to simulate Poisson distributions. For example, to simulate the number of phone calls received by a call center in an hour, with an average rate of 10 calls per hour, we can use numpy.random.Poisson 10, 1000. This generates 1000 samples representing different possible outcomes. Visualizing these outcomes using a histogram can help us understand the distribution of event occurrences. Poisson distributions are widely used in fields like queuing theory to model customer arrivals at a service point, in network traffic to model data packet arrivals, and in epidemiology to model disease occurrence.
While standard distributions like normal, binomial, and Poisson cover many scenarios, sometimes we need to create custom distributions tailored to specific requirements. numpy's random module provides the flexibility to create such distributions. For instance, if we want to simulate a distribution that combines features of both normal and uniform distributions, we can do so by combining samples from numpy.random.normal and numpy.random.uniform. This approach allows for complex simulations that can model unique scenarios not covered by standard distributions. Custom distributions are particularly useful in fields like finance, where asset returns may not follow a typical distribution, or in environmental science, where natural phenomena may combine aspects of multiple distributions. By leveraging numpy's random module, we can create these custom distributions efficiently, providing more accurate models for our analytical needs. Visualizing data distributions is a crucial step in data analysis. It helps us understand the underlying patterns and characteristics of the data. Matplotlib, a popular Python library for data visualization, provides a wide range of functions to plot distributions. One of the most common ways to visualize a distribution is by using a histogram, which shows the frequency of different data ranges. Additionally, we can plot probability density functions, PDFs, to understand the likelihood of different outcomes. By examining the shape of a distribution, we can gain insights into its skewness, kurtosis, and other statistical properties. Visualization not only aids in data interpretation but also enhances communication, allowing us to convey complex statistical concepts in an intuitive manner. Whether you're presenting findings to stakeholders or conducting exploratory data analysis, visualizing distributions is an indispensable tool in the analyst's toolkit. In the realm of machine learning and AI, understanding data distributions is fundamental. Distributions play a critical role in feature engineering, helping to create new features or transform existing ones to improve model performance. Simulating data distributions is also essential for data augmentation, where we generate additional training data to make models more robust. Additionally, statistical distributions help in modeling uncertainties and probabilities, which are crucial for probabilistic models and Bayesian inference. By accurately representing the underlying data distribution, we can improve the performance of algorithms, leading to more accurate predictions. For instance, understanding the distribution of input features can help in selecting appropriate machine learning models and tuning hyperparameters. In AI systems, distributions are used to model user behavior, natural language processing, and image processing, among others. Mastering the art of simulating and analyzing distributions is thus an invaluable skill for anyone involved in machine learning and AI. When simulating data distributions, it's essential to consider edge cases to ensure robustness and reliability. Edge cases refer to extreme conditions or inputs that may not be covered by standard simulations. Identifying these cases early in the simulation process helps in creating more accurate and reliable models. Strategies to handle edge cases include using robust statistical methods that can accommodate outliers and extreme values. It's crucial to ensure data integrity by checking for inconsistencies and anomalies that may affect simulation results. Testing and validation are vital steps in the simulation process. By comparing simulated data against real-world data, we can validate the accuracy of our simulations and adjust parameters as necessary. Handling edge cases effectively requires a deep understanding of the data and the context in which it's used. It's an iterative process that involves refining simulations to capture all possible scenarios, ensuring that our models can handle a wide range of inputs and conditions.
As we work with large datasets and complex simulations, performance optimization becomes crucial. NumPy offers several functions that are optimized for speed and efficiency. It's important to leverage these functions to minimize computational overhead. For instance, using vectorized operations instead of loops can significantly speed up simulations. Another consideration is memory usage. NumPy arrays are designed to be memory efficient, but it's still essential to monitor memory consumption, especially when working with large datasets. Techniques like in-place operations can help reduce memory footprint. Parallel processing is another powerful optimization technique. By distributing computations across multiple cores or machines, we can significantly reduce simulation time. This is especially beneficial for large-scale simulations involving millions of data points. Finally, scalability is a key consideration in performance optimization. Our simulation solutions should be designed to handle increasing data sizes and complexities without a significant drop in performance. By focusing on these optimization strategies, we can ensure that our simulations are not only accurate but also efficient and scalable.
As we conclude our video on simulating data distributions using NumPy, let's recap the key learnings. We've explored how to generate and visualize various statistical distributions, including normal, binomial, and Poisson distributions. We discussed the importance of these simulations in fields like machine learning, AI, and risk assessment. By mastering the skills of simulating data distributions, you can enhance your analytical capabilities and make more informed decisions based on statistical evidence. The applications of these skills are vast, spanning domains from finance to healthcare. As you continue your learning journey, I encourage you to practice these techniques and explore further resources to deepen your understanding. The world of data science is ever evolving, and staying proficient in these foundational skills will open numerous opportunities for you. Thank you for joining us, and we look forward to seeing you in future tutorials.